not least, we report our findings. Scientists that work alone are scientists who don't contribute to science at all. So reporting our findings as we go. Okay. Now we're going to move over to this board and talk about a few other things. One of the things that we're going to have in chemistry is the ability for energy to be able to change from one form to another. So bioluminescence, that's a chemical reaction in which the chemical energy is changed to light energy. Okay, chemical energy is changed to light energy with almost 100% efficiency. Wow, we love that. We love that as chemists. We love that as chemists because bioluminescence, the bottom of the ocean floor, this is some type of organism that glows in the dark. Okay, but even more so important than glowing in the dark, the main part is this chemical reaction where the energy is changed to light energy with almost 100% efficiency, and that doesn't happen very often. The energy in your car, okay, the energy in your car that's changed to mechanical energy, wow, how much of it's changed to heat energy? So we lose a lot of energy. So that's an important thing. That's an important thing as chemists. Let me cover something else too. A really important part of thinking like a chemist. Let's talk about what a theory is. A theory is an idea that is not proven or disproven. Okay, a theory is an idea that is not proven or disproven. So if I have a theory, and this is a pretty good theory, let's say that somebody's going to come to this door at the end of this class and they're going to have a stack of $100 bills and they're going to give us all each a $100 bill. I love that theory, and that's a great theory. And boy, the whole time during class, I'm like, man, that sounds great. Well, it's really good until what? Until I walk to that door at the end of class and I'm looking around. Where's the dude with the $100? There's nobody there. And I'm like, oh, so that theory was proven wrong, so there is no truth to that theory, so it just becomes a nothing. Okay? Now, if a theory is true over and over and over, we might accept it as fact. But I want to pause for a minute and let's talk about a chemist. Okay? Now, really important deal, in high school we study all different kinds of things. We talk about all, biology, chemistry, and all these things, and that's good. But in college, one of the things we're going to learn to do as we take these particular classes is learn to think like a chemist. Learn to think like a biologist. In this class, let's think about a chemist. All right? Now, a chemist can't be opinionated. A chemist can't say, well, I think that acid is really good, or I think that acid is really bad. No, a chemist has to be black and white. A chemist has to say, that acid has a certain amount of acidity. It's a certain molar solution. A chemist says, yes, how will this react? This will explode. Chemist doesn't say, oh yeah, I think that would be a medium explosion. No, chemist has to be black and white. So a chemist does not concern himself or herself with a theory. Biologists do. How old is the Earth? Well, the Earth is 3 to 4 billion years old. Well, that's pretty cool, okay? And scientists say, wow, the Earth is X number of years old. But a chemist says, you know what? If we can't really prove it, it's really not worth the argument. A chemist is somebody who really doesn't like to argue and debate. A chemist is like, I will give you the answer to the best of my knowledge, but if I don't know, I'm going to say, I don't know. So there's nothing against the biologist, and it's important, we need theories, but a chemist is not worried about theories. A chemist is only worried about actual measurements, actual things that happen. So as you take this class, we'll talk about that. A little bit later, we're going to talk about significant figures, and that will tell you a little bit, too, about how a chemist thinks. So what we're going to try to do is go beyond the book, try to teach you how a chemist thinks. My actual degree is in chemistry. I'm actually a chemist. So that's where I think, and that's where my strength is. But we're trying to teach you, if you think like a chemist, this makes a lot more sense than just reading it in a book. So then let's go on to metric units. 95% of the world uses a metric system. It's okay that the United States doesn't. Years ago we tried that. In the United States it's a consumer society. We just didn't buy things that were in kilometers. Okay, we wanted to buy things that were in miles per hour. We put signs up, how many kilometers. People didn't know what it was, and so we stayed with the English units. But the metric units, the only thing you can use in chemistry is metric units because we have to be scaled the same as everywhere in the world. You'll have a quiz a little bit later. The space station, there was an astronaut from the United States that actually tightened up and calibrated, part of the space station using a regular metric. I'm sorry, he did not use a metric socket set. He used a regular American socket set. It was in 7/8 of an inch, whereas it should have been so much in a metric system. And they actually got it out of orbit for a little bit. So we're going to learn about a Mars satellite that we sent out that we used the wrong units, and they used American units, and it actually crashed and cost $5 million. We're also going to talk about a plane in Canada that instead of pounds of fuel, anyway. So the metric system has got to be our standard for chemistry. Let's talk about what this is. The metric unit for length is the meter. The metric unit for mass is a gram. Now, the metric unit for liquid volume is the liter. Now, I want to pause here for a second also, and this is so important to understand. Liter, L-I-T-E-R. Well, what you're going to find is you're going to find a lot of different spellings for words. The original word for liter, okay, is litre, okay, is litre, L-E-T-R-E, and that's Latin. And what happens is in Latin and in French and in Spanish, these are poetic languages. You know, in Spanish we have uno, dos, tres, cuatro, cinco. We have this nice poetic language, okay? And we have the same in French, and we have the same in Latin. But what is the language? What is the language of English? The language of English is not a poetic language, it's a functional language. So in English, we're going to say things, we're going to pronounce things we don't care about. As a matter of fact, if I go around saying I would take a litre of Coke, you might be worried about me, okay? Because you're like, oh my gosh, this guy doesn't even speak good English, okay? So what we do is in English, we have a functional language. So we changed litre to one of them there liters, okay? So as you're dealing with science and you're like, why are the spellings different? Well, they went through the good old American system where we can change a word and we can make it whatever we want. If you are doing Latin, you can't say whatever you want. Okay, you can't make up your own word. In America, I can say, man, this is just honking cool. Okay, and that's okay. But in Latin, you can't come up with your own words. You have to go before a linguistic committee to keep the language the same. So we got to understand the difference. If we talk about an animal with a backbone, that's a chordata. But if we run it through the English system, it's chordate. So as you see words change and you see different spellings, remember it just ran through the English system. The metric unit for energy is a joule. The metric unit for electric current is ampere. Now there's a good example, huh? So what do we say? We don't say an ampere. We say, oh yeah, that's got so many amps. The metric unit for force is the Newton, and the metric unit for pressure is the Pascal. Now, once again, these are the main ones. We'll have a few more as the course goes, but remember, everything is in metric, especially as you do your labs. Everything will be in metric and not anything in the American English standards for measurements. But it's kind of nice because everything is based on tens. So I don't know about you, but years ago when I had to remember how many ounces in a quart and all of that stuff, kind of got confusing, whereas the metric unit is so much easier to convert over. Now, let's move on. Let's talk about something really significant here, okay? Let's talk about significant figures. Now, significant figures in science, remember I was telling you that a chemist, especially a chemist, doesn't want to say, I've got a theory of what this is. I think this is this, or I think this is that. So, in chemistry, when we talk about significant figures, now in math, you may go to your math class and you may be taking college algebra, you may be taking calculus, but on the same token, significant figures might be looked at a little bit different as a mathematician. But once you understand significant figures as a chemist, you'll understand them and you'll get them right and you'll know what we're doing. You can report only what you know. We don't want to guess. We don't want to say, I think it's this or I think it's that. Okay? So for example, if I have a meter stick, okay, if I have a meter stick, and this is 1 meter and this is 2, okay, and I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 lines in the middle, okay, so I can say this is 1.1, 1.2, 1.3, and so forth. But what if my measurement is between those two right there? Oh, so here's 1, and here's 1.1, and here's 1.2. but it's somewhere in the middle. So I say to myself, oh, well, you know, it kind of looks a little bit this side, so let's make it sound really scientific, and let's call it 1 point, oh, I don't know, let's say 1.3. No, a chemist says, you don't know that. Chemist says, that's opinionated. That's a theory. We don't do theories in chemistry. We say, what do we know for sure? So we actually report this. And this will drive you crazy sometimes because you're like, it's more than that. But remember, in significant figures, we report only what we know. So in this case, on a meter stick, this would be 1.1. Even though it's past that, I know for sure I've got 1.1. Okay, 1.1 centimeters on this. So I say to myself, okay, as a chemist, I know I have 1.1. Okay. Now, is it exactly 1.1? No, it's not exactly. What if it was exactly 1.1? How would I know that as a chemist? I would tell everybody in the world that I measured that out. That I knew, for example, it was 1.10 centimeters. Oh, so that's our significant figures telling us exactly what we know. I knew it was 1.1. Okay, now if it was 1.0 exactly, then I would tell you that. Oh, so I only report what I know. Okay, so let's do a mathematical problem here looking at significant figures. All right, so now let's say I measure out 6.5 centimeters times 2.1 centimeters. Okay, so I put that together and I multiply it out, and it comes out to be 13.65. So, do I know that it's 13.65? No, I only measured to one decimal place, the tens place. So I have to round it up to the smallest one. So I have to round this up. 13.65 has to be rounded up to 13.7, and that's my answer. Okay. Now, if you miss this on the lab or you miss this on a test, you'll see this, and they'll put sig. I will put sig fig, and that's what will be marked off, because I didn't measure this to the 100 spot, I just measured it to the tens. So, and we'll talk a little bit more about significant figures. We'll actually have a review for your test. But I will tell you this, significant figures, you always report only what you know. When you're doing a problem with significant figures, you have to report it to the least number of figures that are here. So for example, if I said that I had 6.5 centimeters here and let's say 2.15 centimeters here, and it would change our answer a little bit. But once again, I would still round it to one decimal place, because even though this one has 2, I have to use the one that has the least, because I don't know if that's a 0.50 or a 0.51 or a 0.59. So even though this is the case when this had 2 decimal places, I would still multiply it out, because this has 1 that's the least, then I would make it to 1. Now let's go one step further here, okay? This is why I like this a lot better than a PowerPoint. We can go through these. Let's say I just say it's 6. Let's just say that's 6 centimeters. I don't have it measured to any decimal place, and this is 2.15. Let's just say the answer is still 13.65, okay? So now I say, well, I don't even know, so I've got to do this to the nearest whole number. So right away, that's 6. Remember, if it's a 5 or greater, it's going to round up. So since that's a 6, I'm going to say this is 14. Interesting. Interesting. So I have to report it to the least decimal place. And so it seems a little tricky at first, but the more of these you do, the better you'll get. Now, the last thing that we have in this Unit 1